Okay, well, the rest is very straightforward, but needs to come back to you after a year. So I'm doing it in symbols and so forth. If we do want, I'm going to have you do a couple in numbers, okay? So the process will probably start ringing a bell better than it is right now, but I think I think you're getting it, okay? So, I forget where I stopped recording last time, but I think it was here. Okay, so as a result, the determinant of this matrix has to be has to be 0. We can calculate the determinant of the matrix, right? Since a matrix with determinant 0 won't give us, and it will just give us an AB that's equal to 0, 0, not useful, determinant has to be 0. So we set the determinant equal to 0, and we do the arithmetic, okay?
What would A, B, both being 0, represent?
It represents a solution that's 0, okay?
So
Solution is always 0, the concentration is always 0, it's not relevant to the problem.
so there's no solute at all?
Yeah, that would correspond to having no solute. That's a good interpretation. Catching on. Okay? But if we've got solute, it can't be. Now, actually, yeah, another solution would be no, it wouldn't. No. Okay. I was going to say if your solute's equal, if your concentrations are initially equal, we'll see if that works. Okay, anyhow, determinant of this matrix is just this. It's straightforward. You multiply it out and get the algebra right, and don't copy something down wrong, which I did here. Okay? And fortunately you questioned, but there it is, okay? We notice, among other things, that since we just have the R over V1 and the R over V2 here, we're going to have them here too. And when we multiply these two terms, one of the terms we're going to get is the R squared over V1, V2. But this is going to give us a negative R squared over V1, V2, so those two terms are going to go away. So there's something a little bit unique about this situation. It's not necessarily going to be there when we start having different inflows from somewhere else into these tanks, okay? So when we generalize the problem a little more, that's not going to cancel out, okay? But in this case it does. So we can factor lambda out of what's left, giving us one eigenvalue that's 0. And then from this factor, it's obvious what the other eigenvalue has to be, because this has to be 0, so lambda is going to be the negative whatever this is. So now we've got two eigenvalues. Now we're going to solve a problem for the two eigenvalues. Okay? And this should be familiar. It should be ringing a bell, but, let it sink in. It's not hard. With the symbols, it gets a little messy, but I chose to keep it in symbols. Okay? Would have been easier if I'd had just plain numbers, but then there are relationships that you can see with the symbols that you wouldn't see with numbers. Okay, so if lambda is 0, the equation A minus lambda I times AB equals 0, which is the equation you're trying to solve, becomes this equals 0. Of course, this equals this, so we get this equals 0, right? Now this gives us two equations. This has to be 0, and this has to be 0. But, and it should be familiar if you've solved the eigenvalue problem correctly, or solve the determinant question correctly, get the eigenvalues, you're going to be able to get an eigenvector, because this equation, or this expression, is just the negative of this one. And it'll always be so that this expression is a multiple of this one, if you have a correct eigenvalue. Okay? That's something that should sort of ring a bell, that should come back to you. So anyhow, we get the equation then, negative R over V1A plus R over V2B equals 0. And then another equation which is just R over V1A minus R over V2B equals 0 with the same solution. And we solve that and we get B equals,
It might sound amazing to somebody else, but it just sounds garbage to me. And that's
make
how
sure I
she
got
is
those
about
in the
me.
correct
Which,
order.
you know, I don't understand because she's infinitely.
Yeah. No. Sorry, it's V2 over V1. Now I'm going to look at it again and decide I had it backwards. But yeah, if this is V2 over V1A, then the V2's divide out and you end up with R over V1 and a negative R over V1 here, okay? So, we're going to let AB equal 1. And if A is 1, then B has to be V2 over V1 times 1, which is just V2 over V1. And if I write a 1 down here, which would have been easier since I was down at the bottom of the board, right? Okay? Make sense? So there is one solution. Now, didn't have enough room to write this really coherently. Make it look a little more like the 1 is really in there. Okay?
So what's that bottom matrix?
What's what?
What's that bottom row represent?
It represents, well, you're going to see in a minute. Okay? Okay, so this is a solution. Now, it's a solution to the equation x prime equals ax, which is equivalent to this. So it's a solution to this equation. A solution being an AB, okay, that makes this equation true. And you go back to the original equation and substitute that just to double check, but it's going to work. I'm not 9% sure. Okay? So AB is this. V2 over V1. Not thinking. But this is a solution. To our equation, x equals x prime equals ax. Just to remind ourselves now of what x means. It's the Q1, Q2 vector. Okay? And from this we conclude that, well, so 1 V2 over V1 is one member of our solution set. It's one possible solution. The other member of our solution set is the one we get for this eigenvalue.
Yeah.
Now we're getting two solutions, even though it looks like a first order equation, because it's a first order equation in two-dimensional space, on two-dimensional vectors. Okay? And there are things you do with the Wronski in a two-dimensional. A lot of this stuff is so analogous to what you've already learned. Okay? Another thing we can say is we could take this system of equations and express it as a single second-order equation. Now, we might not get to that, but just to put it in context, we're going to expect two solutions. Okay? Because this system is equivalent to a second-order equation, but also because you have two equations and two unknowns, basically. Okay? And I'm waving my hands on that a little bit because we're not going to have time since the course has been dumbed down by a credit. Okay? Which is why I'm going a little easy on you. Just imagine where you'd be if it was a 4 credit. We'd be almost done with this stuff. Okay? There's a lot of neat stuff about this, like variation of parameters is much easier for systems than it is for second and higher order equations, okay? And it's really neat the way that works out. And then there's a lot of other stuff that I just love to do and have always loved to do, but I'm not going to make you suffer through it.
Oh.
You can always look at videos from previous semesters if you get curious or if you need it. Of course, I've got to look at what your transfer institution really wants you to have in this course. Okay? The main thing they want you to have is good command of stuff up through second order and higher order equations. And higher order equations is just a trivial extension of second order equations. Everything just translates over beautifully. The existence proof is a little more complicated, but we're probably not going to do that. Other than that, the methods are completely the same. Anyhow, we want to finish solving this. Okay, so for lambda, equals r times 1 over v1 plus 1 over v2, negative r times 1 over, negative sign there. God, now it looks like another equal sign. Okay, negative r times this, okay? What's our equation become? Well, we get it's r over v2. Then it's r over v1. Then it's negative r over v2 minus, and I have no idea, I do have an idea why I put that there, because I've put the negative in the wrong place. Actually, I needed it here, but I needed parentheses there. Okay? And I didn't put the parentheses there, which was mine. And that should be an R. I'm thinking too much instead of just copying stuff down. But I do that wrong too. Okay? Make sense? Now I've got the signs right. The other thing I was really looking at is just that this and this add up to 0. As do this and this. So all we end up with is this. Okay? And that's supposed to equal the zero vector. And this just becomes then r squared, and I've got a wrong thing in here.
I think the top
That's
left.
r over v2. And of course, that's going to be inconvenient, because that's going to give you 0, right?
I missed that day.
And I've left off my AB here, and my AB vector here. And the conclusion then is these coefficients are both the same in both cases. So when this is multiplied out, you just get A plus B equals 0. And you can fill in that stuff if you don't see it instantly, but it's fill in the steps and then you say, oh, duh, you know. Okay? Now, I've kind of glossed over something before. So 1, -1, or any constant multiple thereof is a solution. Okay? Thus, e to the lambda t, which is e to the -r times 1 over v1 plus 1 over v2 t times 1 -1 is the other element. In our solution set. And our solution set is then just 1 v1 over v2, v2 over v1. I have it right now. E to the -r times 1 over v1 plus 1 over v2, written a little small, but it's the same thing we've got here, times 1, -1. That's our solution set. All the solutions of this equation are linear combinations of these. So, abbreviating it, a vector function is a solution if and only if it's a linear combination of these. Okay? That's written kind of badly, but if you work it out, you see exactly how it needs to be. Okay? So that's the idea. And that's the method you use in solving any system of two linear equations. Okay? So you can look forward to chapter 6. The first time you see a matrix, which is like on the first problem, use this method. And it's simpler because you're going to have numbers instead of symbols. The symbols tell us stuff, though. This 1 over V1 plus 1 over V2 is a recurring form, like a 1 over X plus a 1 over Y, or 1 over A plus a 1 over B. You're going to see it in physics. In parallel circuits, or series circuits, series capacitors. Okay? It's real easy though. Okay? There's a little more to it here. But that's the scheme. You've got to understand that much. And once you do, the rest of it is not very difficult. Okay? Take a good look at it.